Today we're going to look at the first lecture of chapter number 9 and the learning goals for today's lecture. The first one, to describe rotation in terms of angular coordinate, angular velocity, and angular acceleration. And the second is to analyze rotation with constant angular acceleration. As an introductory slide here, we talk about wind turbine, it's rotating, CDs, and no one basically seeing CDs nowadays, or those who still have fans in the ceilings, Ferris wheel. All of these objects involve rotating rigid bodies, and we'll explain what we mean by rigid here. Now, real-world rotation can be very complicated because of stretching and twisting, of the rotating body. But today, we're going to assume that the rotating body is perfectly rigid. That means the point which is rotating on the body will stay in its place. It's not going to move. So we assume that the body is rigid, it's hard. So there is no twisting, no stretching, none of these effects. So the object stays as hard as it is. Now, we're going to look at how to describe this rotation. And first, we're going to look at angular velocity and angular acceleration. But when it comes to rotating bodies, so to describe this rotation, so for example, on the x-axis here, this is your x, this is your y, you have here an object. Let's concentrate here and point P on this rigid object. And it is rotating around an axis. Now, this is the x-axis, this is the y-axis, the z-axis will be pointing out of the screen in your case. So now, usually when we did this in chapter number 1, when look at a point, we describe its x and y positions. But when we talk about rotation, we're going to describe this point here in terms of r and theta. Now, we made an assumption that the object is rigid object. So this point P here is not going to change its position. So relative to the axis of rotation here, which is the z-axis, this length is not going to change. It's going to stay constant in this case. So now what is going to change is basically the angle that the object is rotating through, which is theta. And if this object is rigid, all of these points, if you pick any points along this line here, they're all going to stay in their location as the object is rotating. So the r for them, or how far they are from the center, it's not going to change. But what's going to change is the angle through which they rotate. So we're going to look at this angle here, theta, and we call this the angular position. Now, we are going to look when you are rotating this way relative to the positive x-axis. Remember, in chapter number 1, we measured the angle relative to the positive x-axis when we talked about vectors. Now, if you have a clock in front of you, you will see that the clock rotates this way. Now, you're rotating this way. That's opposite to the direction of the clock. And we call this contra clock clockwise. So if you take here C for clock, and W, so we say the CW, counterclockwise. So you're basically this way, it is counterclockwise. And this way it is clockwise when you go with the clock. So usually we take the position positive if it's measured in the counterclockwise direction, which is relative to the positive x-axis. So we're going to assume that the object is rigid. It is rotating around an axis. And in this case, the rotation is around the z-axis, but the object is in the xy plane. And we measure the angular position theta relative to the positive x-axis. Now, what units we're going to use for these angles? You're all familiar that you measure angles in degrees. And when you go a full circle, you have 360 degrees. Now, that's a circle. That's the center of the circle here. That's your radius of the circle. Now, there is a definition that we're going to use for a unit that we're going to call rad, which is radian, and we're going to measure the angle in terms of these units here, the SI units. Now, what is the definition of rad? Well, if you go an arc around the circle, let's call it S, and if this arc is equal to R, in that case, we define theta as S divided by R, and since S is equal to R, so R over R gives you 1. So actually you get 1 rad when the arc that you go through is equal the radius of your circle. Now, from high school, you know that when you go around the circle, you say that the circumference of the circle is equal to 2 pi r. Or in general, we can say that S is equal to R theta. And when you go around the full circle, this will equal to 2 pi, and that's why the S is going to equal to 2 pi r. So in general, we define theta as S divided by R, between the arc divided by R, and we measure that in radian. So it's equivalent to saying that S is equal to R theta. So if you measure theta and you know the radius, you can basically know the circumference of the circle or the part of the circle that you go around. In one complete revolution around the circle, S will equal to 2 pi r, because the theta here will equal to 2 pi. So your circumference will equal to 2 pi r. So 2 pi, it's equivalent to 360 degrees. So 1 rad here will be 360 degrees divided by 2 pi, which equal to 57.3 degrees. So you can look at a 1 rad in 2 different ways here. It's equivalent to 57.3 degrees, or the arc that the object goes around in equals the radius of the circle. So that's what 1 rad is. And we measure angles in terms of radian. Is this clear? Any question on this? So now, when we look at a rotating body, and in this case, we're going to look at, let's say, if you pick point P here, and it's going to rotate. Now, we can measure the angle that it makes relative to the positive x-axis. So if I look at T1, I will measure an angle which is equal to theta 1. So at T1 here, you actually measure an angle theta 1. If you look at the point at t is equal to 2, you will find that it makes an angle theta 2. So at T2 here, you make an angle theta 2. So actually, what you're measuring angular position. And this angular position is measured in units of radian. So you actually, at T1, you are at angular position theta 1, and at T2, you are at angular position theta 2. Like what we did in chapter number 2 when we talked about linear displacement. We're going to talk about displacement here. We're going to say angular displacement. And the angular displacement here will be delta theta, which is theta 2 minus theta 1. If you recall, in chapter number 2, we talked about delta x, and we said delta x is equal to x2 minus x1. But here, we're going to look at the change in the angular position of the point or the particle on the rigid body. And this is what we call angular displacement. Now, we're going to define something that we're going to call average angular velocity. If you recall, when we did that in chapter number 2, we said Vf dash x, that means along the x-axis, it should equal to delta x by delta t. So here we're going to define angular velocity, and we're going to use the symbol omega for angular velocity. So we say omega f, and that omega f should equal to delta theta by delta t. Of course, it is theta 2 minus theta 1 over t2 minus t1. Now we're adding here dash z. Here, if you recall, in chapter number 1, we said x because it was along the x direction. Here, we say it is along the z. What do we mean by this? Now, the plane that your object in, it's x and y. But it is rotating around the axis, which is perpendicular to this. So you have x, y, and z. So the rotation is around the z-axis. And that's why we put the z here. So we say omega fz, that means the average angular velocity around the z-axis. It will be delta theta by delta t, which is theta 2 minus theta 1 over t2 minus t1. And that's what we say here. The subscript z means that the rotation is about the z-axis. So usually rotating bodies in a plane, and in this case it's the xy plane, and the rotation around the z-axis. Now the units for the average velocity here, it will be rad per second. Now, as we did in chapter number 2, when we said that the Vx should be in the limit as delta t goes to 0 of delta x by delta t, and we said this is equal to dx by dt. We're going to do the same thing here. We're going to talk about instantaneous angular velocity. And we'll do that in the limit as delta t goes to 0 of delta theta by delta t, which is d theta by dt. So we take it in the limit as delta t goes to what, or tends to 0. Is this clear? We're not doing anything new. We're following what we did previously here. And of course, here we take the subscript f out and we put only omega z. And the reason we have the z here because the object is in the xy plane and the rotation around the z axis. Is this clear? Now, rotation. When the rotation is counterclockwise, and you take here C, C, W, and we say the CCW, counterclockwise. That means you're moving from the positive x-axis. Now, when you do that, you know that your theta 2 is going to be greater than theta 1, so your delta theta will be greater than 0. So in that case, your omega fz will be greater than 0. That's when you're rotating counterclockwise. Now, if you rotate the other way, which is now you omit the counter and you just say clockwise, so it is CW here, clockwise. You know that in this case, your theta 2 is going to be less than theta 1. And that will tell you that the delta theta will be less than 0. And of course, the omega f along that direction will be less than 0. So that's one thing that you have to keep in mind, in a similar fashion to what we did when we talked about linear motion or motion in straight line in chapter number 2. Now, we extend that to the instantaneous angular velocity. So we say that omega is greater than 0 in the direction of increasing theta. And omega is less than 0 in the direction of decreasing theta. That's when we talk about the instantaneous. And of course, we don't have f. We just talk about theta here, omega here. Now, what are the units of omega? Well, the units of omega, as we discussed, is rad per second. But there is also a unit that is commonly used, which we call revolution per minute, which is RPM. So R for revolution, P here for per, and minute. Okay, so we call it RPM. And you can convert from rads to second to revolution per minute, because you know that one revolution contains 2 pi rad. And of course, you know that the minute contains what? Contains 60 seconds. So that's another unit that we use, but usually, since this is used a lot, you find yourself that converting RPM to rad per second to use it in the equation. Is this clear? Now, how would you look at the direction of the angular velocity? Because the angular velocity here will be considered as a vector. So you're going to use the right hand rule. And the right hand rule tells you that you curl your fingers in the direction of the rotation. So the rotation here is counterclockwise. Your thumb will be pointing in the direction of your angular velocity. So if we follow what we have been doing so far, so if this here is the x-axis, and this here is the y-axis, and this will be the z-axis, actually this body here is in the xz plane, and it's rotating around the y-axis. And in this case, we say it is, if we want to talk about omega, we'll say omega y, if we follow this convention that we're following so far. So it is, the direction of it is along the positive y-axis. Now, if it is rotating clockwise, this way, well, when you try to curl your fingers, you find out that's the only way that you can curl them, and the thumb will be pointing where? Will be pointing down. You're still rotating around the y-axis, but in this case, we'll say the negative y-axis. Is this clear? So that's how you decide on the direction of your angular velocity as a vector. All right, let's deal with examples here. And the example that we have is example 9.1. The angular position theta of a 0.36 meter diameter of flywheel is given by theta equal to 2t cubed. And they ask us here in A, find theta in radians and in degrees at t is equal to 2 seconds and at t is equal to 5 seconds. So theta 1 is evaluated at theta of 2 seconds. So it's 2 times 2 raised to the power 3, which is 2 cubed, and 2 cubed is 8, and 8 times 2 will give you 16 rad. So now this is your theta 1 at 2 seconds. Now they want us to do it in degrees as well. You know that 360 degrees in 2 pi. So this will give you 916.7 degrees. So that's your theta 1. Theta 2 is evaluated when t is equal to 5 seconds. So it's 2 times 5 cubed, and 5 cubes is 5 times 5 times 5, which is 125. And 125 multiplied by 2 will give you 250 rads. Now you can convert this into degrees by multiplying 250 by 360 divided by 2 pi, and that will give you 14,023 degrees. And that's how we calculate the theta 1 and theta 2 at t 2 seconds and t is equal to 5 seconds here. B, find the distance that a particle on the flywheel rim moves over the time interval t equal to 2 seconds to t is equal to 5 seconds. So you look at your flywheel and you want to look at a particle on the rim. So you're basically having the radius there. Remember what we said, that S is equal to R theta. So your S here will equal to R delta theta. And of course, your delta theta here will equal to theta 2 minus theta 1, which is 250 minus 16, and it will give you 234 rads. Now you have to find the radius. They give you the diameter here, which is 0.36 meters. You take half of that, that will give you the radius, which is 0.18 meters. So the distance through which the particle on the rim moves will be 0.18, which is the radius, multiplied by delta theta, which is 334 rad, and that basically gives you 42.1 meters. Is this clear? Any question on this? We continue with the same example, but in C here, they ask you find the average angular velocity in revolution per minute over the time interval. That means from 2 to 5. We know that the omega average, that's Z, because we take the Z-axis as the axis around which the flywheel is rotating. Delta theta by delta t, which is theta 2 minus theta 1 over t2 minus t1. 250 minus 16 over 5 minus 2. That gives you 3. So 234 divided by 3, that gives you 78 rad per second. So this is now your average angular velocity. Now they come and they want it to be in revolution per minute. So you know that each revolution contains 2 pi. So if you divide 78 by 2 pi, it will give you the number of revolutions. And you know that the second is 1 over 60th of a minute. So it is divided by 2 pi, multiplied by 1 over 60 to make it in minutes. That's equivalent to saying it's 78 times 60 divided by 2 pi, and that will give you 744.8 revolutions per minute. Remember when we talked about unit conversions in chapter number 1. So here 78 rad per second is equivalent to 744.8 revolutions per minute. And many times you find that if you're given something in RPM, which is revolution per minute, you have to convert it to rads per second. In D, find the instantaneous angular velocity. Now, angular velocity, instantaneous, or we just say angular velocity, it means at a certain instant. So they want it at t is equal to 2 seconds and at t is equal to 5 seconds. Now here we say omega z. We take the f out because we're talking about instantaneous. Now it should be d theta by dt. So you're going to differentiate theta here with respect to t. So you have t cubed here. And the differentiation of t cubed will be 3t squared. And you have a 2 here. So 2 times 3 will give you 6. So it's equal to 6t squared. And that's now your instantaneous angular velocity. Now you can evaluate that at 2 seconds. That's why we say omega z of 2. It's 6 times 2 squared, and 2 squared is 4. 4 times 6 will give you 24 rad per second. Again, you can convert this to revolutions per minute if they ask you to do so. Now, omega z of 5 will equal to 6 times 5 squared. 5 squared is 25. 25 times 6 will give you 150 rad per second. So that's how you look at average angular velocity and instantaneous angular velocity. Any questions so far? Is this clear? Now, like what we did in linear motion in one dimension, we talked about average acceleration, and we put x, and we said this is equal to delta vx by delta t. So here we're going to look at average angular acceleration, which is the time rate of a change in the angular velocity. So we say alpha, and we're going to use a symbol alpha. So for angular position is theta, omega for angular velocity, and alpha is for angular acceleration. So we say alpha f z, and z here meaning around the z axis, it will equal to delta omega z by delta t, which will be omega 2z minus omega 1z over t2 minus t1. And this basically gives you your average angular acceleration. Now, you can look at the figure that we have here. That's at t1. And you look at the curved arrow that's representing omega 1z. At t2 here, and you look at the curve arrow here that represents the omega 2z, and you'll find that the omega 2z here is greater. So this value coming here, it's a positive value. And that's why the alpha z will be in the direction of the positive z-axis. Now, we can take alpha z instantaneous here, what we call instantaneous angular velocity. And will we do that in the limit as delta t goes to 0 of delta omega z by delta t, which will be basically equal to d omega z by dt. That will give you your instantaneous angular velocity. What are the SI units for it? It will be rads per second squared. We are not doing anything new. We're just following the logic that we did in chapter number 2, but we're now going from angular position, angular velocity, angular acceleration. Now, if you look at what we have here at t1, that's your omega 1z, At T2, that's your omega 2z. So omega 2z is bigger than omega 1z. So you know in this case that your omega in both cases is going counterclockwise. And counterclockwise, that means your omega is greater than 0. Now, if you want to get your alpha, which is delta omega by delta t, since omega 2 is greater than omega 1, you know that you're going to get a positive value as well. So the alpha here is greater than 0. And since omega 2 is greater than omega 1, you know that you're actually increasing your angular velocity. If you take the magnitude, that means it's the angular speed. And since the alpha is greater, so both of them are in the same direction. And in this case, you are speeding up. Now, if you look at the cartoon that we have, that at T1, now they give you omega 1z. And at T2, they give you omega 2z. Look at the curved arrows here. Omega 2z is less. Okay. But both of them counterclockwise. That means omega is still greater than 0. But if you want to look at your alpha, which is delta omega by delta t, you know that's going to be less than 0 because omega 2 is less than omega 1. And that's why we say that the alpha here is less than 0. Less than 0, that means you're slowing down because actually you went from a higher omega 1 to a lower omega 2. That means you're slowing down. And in that case, your angular acceleration is less than 0. So if we look at this in terms of vectors, so in terms of vectors, when your omega and your alpha are in the same direction, then the rotation is speeding up. But when your omega and your alpha opposite directions, then the rotation is slowing down. We've seen something similar when we talked about motion in one dimension in chapter number 2, when we said the velocity and acceleration in the same direction, you'll be speeding up. If the velocity and the acceleration are opposite each other, you're slowing down. Is this clear? So let's take an example here. It's the same example that we dealt with, where theta is expressed as a function of time and theta is equal to 2t cubed. They ask us, find the average angular acceleration between 2 seconds and 5 seconds. You know that your average angular acceleration, it's going to equal to delta omega by delta t. So it's omega 2z minus omega 1z over t2 minus t1. In the previous example, we already calculated at t 2 seconds, omega 1z is equal to 24 rads. At t is equal to 5 seconds, omega 2z was equal 150 rads. We have to add here second. Okay. So now when you do that, it will be 150 minus 24 over 5 minus 2. So this will give you 126 over 3, and you get 42 rads per second. And that's now your average angular acceleration. In D, they want the instantaneous angular acceleration. And the instantaneous angular acceleration is d omega by dt. We have here omega z will equal to d omega z by dt. So if you recall that we said that omega z was equal to d theta by dt, and that basically was equaling to 6t squared. So now we say d omega by dt, which is d by dt of 6t squared, and the differentiation of t squared is 2t, so you multiply 2 by 6, you get 12t, and that's now your alpha z here. If you recall what we did in chapter number, omega z is equal to delta theta by delta t, and alpha z here will equal to delta omega z by delta t. So alpha z will be delta by delta t of d theta by dt, which is equal to the second derivative of theta with respect to t, which is exactly what we did here. So now they want the instantaneous acceleration at 2 seconds. So alpha z of 2 seconds, it's 12 times 2 and gives you 24 rad per second squared. And alpha z at 5 seconds will give you 12 times 5, which gives you 60 rads per second squared. Is this clear? In chapter number 2, we developed kinematic equations for one-dimensional motion or motion in a straight line, but we invoked one condition where we said that the acceleration is going to be constant, and we developed the following equation: Vx is equal to V0x plus AXT, x is equal to x0 plus V0xt plus 1/2 AXT squared, and Vx squared is equal to V0x squared plus 2AX times x minus x0, and x minus x0 is equal to 1/2 Vx plus V0x. We're following the same argument. So we're going to assume that we have constant alpha z, and if we do that, we will get the similar set of equations, but instead of Vx, we'll see omega z. That's our angular velocity now. It should be omega z equal to omega 0 z plus alpha z t. Theta, that's our angular position. Here we have linear position x. So theta should equal to theta 0 plus omega 0 t plus 1/2 alpha z t squared. And then we have omega squared equal to omega 0 z squared plus 2 alpha z times theta minus theta 0. And theta minus theta 0 is equal to 1/2 omega z plus omega 0 z times t. So you're getting the same set of equation if we have constant angular acceleration. Is this clear? We're not going to go through the, we'll just apply what we have done before. Is this clear? So we can apply that to an example here, and we're going to deal with example 9.2. You have finished watching a movie on Blu-ray. The disc is slowing to a stop. The disc's angular velocity at t0 is 27.5 rads per second, and its angular acceleration is minus 10 rads per second squared. The line PQ on the disk surface lies along the positive x-axis at t is equal to 0. So you look at this line here, and this is what you take at t is equal to 0. Now they ask you, what is the disk's angular velocity at t is equal to 0.3 seconds? Well, you're going to use this equation here, alpha z equal to, because they tell you it's constant acceleration. So that's why we say they say constant here. So omega z, it's equal to omega z0 plus alpha z t. Your t is 0.3. Your omega z is what you want to find. And of course, your alpha z is constant, and it's equal to minus 10 rads per second squared, and your omega z is equal to 27.5 rads per second. So you plug in for omega 0 z 27.5 minus, you have a plus, but alpha z is minus 10. So it's minus 10 times 0.3, and this gives you 24.3 rads per second. In B, what angle does the line PQ make with the positive x-axis at this time? Well, you want to see the angular position. So you're going to use the equation theta is equal to theta 0 plus omega 0 zt plus 1/2 alpha zt squared. And I remind you, the disk is in the xy plane. That's why the rotation is around the z-axis, and that's why we use the symbol subscript z for omega here and alpha. Now we choose theta 0 to be 0 at t is equal to 0, and omega 0z, they tell us that t is 27.5. You multiply that by 0.3 minus, because the alpha is minus 10, minus 1/2 times 10 times 0.3 squared, and that gives you 7.8 rads. So that's basically how much you covered. Now they ask you, the line makes an angle what with the positive x-axis? Is it below? Is it above? Okay. So you know that one revolution is 2 pi. So if you look at the number of revolutions here, 7.8, and you divide that by 2 pi, this basically gives you 1.4 revolutions. So this line here has gone one full revolution and then 0.24 of a revolution. And this is the angle now that you want to find relative to the positive x-axis. So when you do that, you're going to multiply 0.24 revolution multiplied by 360 degrees divided by revolution, and it gives you 78 degrees. So now it makes an angle of 78 degrees. So you have to be careful here. What you calculated is basically calculated the theta that it goes through, but they ask you what angle does the line make with the positive x-axis. So if this number here exactly comes as 2 pi, if this one here comes as 2 pi, then you will basically going to get 0. But you have to see how many revolutions. And then you look at the difference and you multiply that by 360 degrees, and that will give you the angle relative to the positive x-axis. Is this clear? Now, let's take a few questions, as we usually do, to try to test some of our understanding. The graph shows the angular velocity and angular acceleration versus time for a rotating body. At which of the following times is the rotation speeding up at the greatest rate? So you know that when your omega is greater than 0 and your alpha is greater than 0, you're going to be speeding up. And when your omega is greater than 0, but your alpha is less than 0, in that case you are slowing down. By the way, when your omega is less than 0 and your alpha is less than 0, you're also going to speed up, because your angular velocity and angular acceleration in the same direction. And when your omega is less than 0 and your alpha is greater than 0, in that case you're going to slow down. Now you start for your alpha here. Alpha is positive value, is greater than 0 all the way up to 2, and then it becomes less than 0. Your omega here, it's greater than 0 all the way up to 4. So if you look from 0 to 4, your omega is greater than 0. But your alpha is actually up to this point here, it is what? It is negative, and then basically it starts going in the negative direction. So at 4 here, or before 4, you have omega is positive, but your alpha is negative. But if you look at 5 here, your alpha here is negative and your omega is negative. And this is the biggest for alpha. When alpha gets bigger and bigger, that means the change is bigger and bigger. And that's why it will be at the greatest rate at t is equal to 5 seconds. Is this clear? So here you can say speeding, and here slowing, same thing, speeding, and here slowing. Okay, is this clear? In this question here, a DVD is initially at rest so that the line PQ on the disk surface is along the positive x-axis. The disk begins to turn with constant alpha equal 5 rads per second squared. At t is equal to 0.4 second, what is the angle between the line PQ on and the positive x-axis? Like what we did in the example, you're going to say that theta equal to theta naught plus omega 0 z t plus 1/2 alpha z t squared. You can take theta 0 to be 0. They told you you're starting from rest, so this one will go to 0. So you have 1/2 alpha z t squared. So this will equal to 1/2. Your alpha is 5, and your t is equal to 0.4 squared. 0.4 squared will give you 0.16, and 5 times 0.16 will give you 0.8, and 0.8 times 5, this will give you 0.4 rads. So this is less than a revolution. So the angle that it makes with the positive x-axis is 0.4 rads. Is this clear? Is this clear? So we're just trying, in this lecture, we try to look at how you can express points on a rotating body. You're not going to use x and y, you're going to use r and theta, and you're going to talk about angular position, theta, instead. And then you're going, and by the way, when a body is rigid and it's rotating, if you have a body, and this is the axis of rotation here, well, every point will have a different r, but all these points, because the body is rigid, they will all rotate at the same theta. And that will basically give you the same angular velocity, which is d theta by dt, and the same angular acceleration, which is d omega by dt. And if we take the case when the angular acceleration is constant, we developed a set of equations similar to the ones that we had in the motion along one dimension. Omega z is equal to omega 0 z plus alpha z t. Theta is equal to theta 0 plus omega 0 z t plus 1/2 alpha z t squared, or omega z squared equals to omega z squared equal to omega 0 z squared plus 2 alpha z theta minus theta 0. and theta minus theta 0 is equal to 1/2 times alpha plus alpha z0 times t. And this basically the end of today's lecture. Any question on these? Any questions on these? In the next lecture, we'll try to relate linear motion to rotational motion. Okay. Is this clear? Is this clear? Any questions on these? Good.